Continuando com o nosso evento, convido a professora doutora Alexandra Sasha Rich McLarty para ministrar a palestra Making a Hidden Resource Visible. A professora Sasha é professora assistente na Universidade Estadual de Washington, em Pullman, no Departamento de Engenharia Civil e Ambiental e co-diretora do Centro de Pesquisa, Educação e Divulgação Ambiental. Sua pesquisa utiliza uma diversidade de ferramentas e dados para responder 3 questões principais: quanta água temos, quanta água usamos e quanta água precisamos. A doutora Rich obteve seu doutorado em Engenharia Civil pela Universidade da Califórnia em 2014, onde utilizou sensoriamento remoto por satélite da missão GRACE da NASA para quantificar o estresse hídrico nas maiores sistemas aquíferos do mundo. Ela também possui bacharelado em Engenharia Civil, com foco nos estudos ambientais e de água pela Universidade de Stanford.
Muito obrigada. Vou fazer uma introdução em português e depois a palestra em inglês, tá bom? Estou muito feliz de estar aqui no Brasil e em Rio Claro. Eu estudo as ciências hidrológicas por causa do Brasil. O meu pai é cientista e ele estudou o Rio Amazonas para 50 anos ou mais com colegas em Sena, em Piracicaba. Então, eles estudaram o rio mais grande do mundo. É muito impressivo. Mas eu acho que é mais difícil para estudar as águas subterrâneas. Pode ver os rios, pode nadar, pode coletar amostras de um barco, de a praia para os rios. Mas não pode fazer essas coisas com as águas subterrâneas, né? Então, hoje vou falar sobre essas águas mais difíceis. Vou falar em inglês agora. Se estou falando rápido demais, fala devagar, tá bom? Okay, thank you. Okay, so today I will mostly talk about my research in the Columbia River Basin in the Pacific Northwest of the United States, and I will end a little bit on work my students and I have done, but not published yet, in Brazil and near Brazil. So we will start with a little history lesson about my area. I call it my aquifer. I don't own it, but it's mine to study. And then we'll talk about how to study it first with people and with wells, and then with satellite remote sensing with GRACE. Let's go. So, start with people, then using satellites for how to make a hidden resource visible. I use models. I am not a modeler, so we use models in support of some of the research we do, but my primary focus is on using data collected by people and collected by satellites. Okay, this is my study area. And normally in hydrology, when people talk about the Columbia Basin, they talk about this. This is the Columbia River Basin. I live around here, Seattle is around here, and Vancouver, BC is up here. It's a very large river basin, but what I study is this Columbia. This is the Columbia Plateau Regional Aquifer System, or the CPRAS. It's right in the middle of the river basin. And interestingly, all of the cropland area, almost, for the Columbia River Basin is also within the aquifer system. So all of the area in pink here, all of this area in pink is cropland, and the aquifer is outlined in black here. Now, Washington, my state, is very famous for apples and wine grapes and hops to make beer. All of these things we're famous for are grown on top of my aquifer. We think that about 25%, 35% of the irrigation water for this area is derived from groundwater, even though people always only think about the surface water. We think with climate change, our snowpack will decline, making surface water less available, and the dependence on groundwater will increase. Okay, let's learn a little bit about the aquifer system. This is a cross-section from right in the middle of the aquifer. And first you see its size, 44,000 square miles, closer to 90,000 square kilometers. And the interesting thing about this aquifer is we were talking about how to represent an aquifer like a layered cake. So the cake of this aquifer has 4 main flavors, 4 main layers. So we have the overburden up here in yellow. This is unconsolidated sedimentary material, the unconfined aquifer, and everything else is fractured basalts. And they all behave as confined aquifers. And you notice this big block here. You can't read the y-axis on this, but in the middle of the aquifer, this layer, the Grand Ronde layer, goes down about 500 to 600 meters. We're not drilling groundwater from that deep for the most part, but it is a very extensive groundwater system. So this is a geology department mostly. I will do with you what I do with my students. If you feel comfortable with unconfined aquifer versus confined aquifer, give me a thumbs up. If you don't, give me a thumbs down. If you don't know what I'm saying, look confused. Yeah? Okay, so this is just the basics. When you have an unconfined groundwater system, you lose storage from right at the aquifer. If you have a confined system, then the water level in the well represents a head, potentiometric head. And when you pump from that system, you lose groundwater from somewhere else. And often we don't know where. And so it's important to understand the difference between confined and unconfined dynamics for the work that we will go over. Okay, so here's a history lesson. This area, this big blob in green, right here, is right in this area of Washington State. This area is called the Columbia Basin Project, and it was created by building the Grand Coulee Dam, which is a huge hydropower dam. And the goal of this project is to irrigate 1.2 million acres of agricultural land. When it was built, that was the goal. In the 1960s, an economist at my university now said the project did not have the right cost-benefit ratio. It cost too much for the benefit of expanding irrigation with surface water. But many farmers had already been farming this land, and instead of receiving the surface water, they were issued temporary groundwater permits in the early 1960s. Those temporary permits are still in use today, and we have observed water level declines on the order of 3 meters per year in much of this area. And so we have a big issue with what the future reliability of groundwater will be in these deep confined layers. And this is important from an economic perspective. So McDonald's, who you may have heard of, grows many of their potatoes for French fries in this area. So, long story short, no water, no French fries, right? Okay. No McDonald's, which maybe would be fine, but that's a different topic. Anyway, okay, so the part of this aquifer that is so interesting to me is all of the different layers and understanding how things are different in the different layers. Are we observing the same water level declines, the same vulnerabilities, and so on. So this is a paper from 1974, and even then we had an understanding that this aquifer had different layers and that the water levels were doing different things. So they called the upper layers aquifer zone A that had some decline, but not too steep. Then we had aquifer zone B, where you see higher seasonality. And in both of these layers, the water level is declining. So this is already being observed back in the 1970s. So our research right now is trying to understand what the historical trends have been across all of those 4 aquifer layers, the yellow, the blue, the pink, and what the future vulnerabilities might be. And then the next question is, are our satellites able to quantify the changes in this aquifer system that, again, is a mostly confined system? We'll start here. Okay, the first thing to provide context for this project, the results that I will show in a moment are part of a large project in the state of Washington. The Department of Ecology is our state agency that manages surface water and groundwater. So if you want to pump groundwater, you have to apply for a permit to use that water from the Department of Ecology. And our state legislature in 2006 said this department has to do a water supply and demand report every 5 years to estimate current and future water supply and demand. So that was in 2006. In 2021 was the first year we really had groundwater incorporated into this report. Previously, it was just focused on surface water. So we did a historical analysis, and then this report is theoretically used by the state legislature and state agencies to make decisions about investment in water infrastructure. So this is one way that we can connect the science we do at universities with decision-making and management of groundwater and surface water. One great thing about studying my aquifer is that we have quite a bit of data available. So this is now just the eastern portion of Washington State. And actually, let me go back here. It's just, if you cut a line sort of right here, this is the study area. Oh no, I have it in black. This outline in black is the domain or the study area for the results that I will present. So the Department of Ecology, our state agency for managing water, collects groundwater data every year in the springtime. So for us, if you have a groundwater right to pump irrigation water, that right you can start using in March or April. And then the growing season goes through the summer for us, June, July, August, September. And then somewhere around October or November, you have to stop using your water right. So you stop pumping groundwater, and then it rains and snows and the aquifer recharges and rebounds from finishing pumping. And so then in the spring, before you start pumping again, the aquifer is theoretically at a static level or an equilibrium level. So ecology monitors our groundwater in the spring to track long-term trends in groundwater storage. So we first defined these sub-areas in white. And they are areas that we hope represent hydraulic connectivity. In the same way surface water has watersheds, right? Everything inside a watershed is connected. We tried to create areas where theoretically the groundwater dynamics would be connected, even within a single aquifer system. We have many faults and folds and fractures and flow barriers and preferred pathways in our aquifer. So even though it's part of one big aquifer, there's a lot of difference in water levels from location to location. And as you know, groundwater data is very private, and often people do not want their groundwater data to be shared. And so all of our results we averaged within each of these sub areas. So we didn't publish a report that somebody could say, hey, my neighbor is using more water than me. Look at the results of this state-funded paper, right? We do not want that to happen with our results. So we aggregate to these sub areas. And then the different colored dots here represent the different aquifer layers. So any dot that is in red represents a well that has been opened to that deep Grand Ronde layer. Many of those wells are 50 to 300 meters deep. And so they're protected from the surface, right? Contamination, but it's harder to supplement water supplies in those deeper layers. This is where I live, right here in the Palouse Basin. So all of our groundwater that we use in the city comes from the Grand Ronde layer, quite deep. So what we did is we first of all downloaded well logs for every one of these wells that we had water levels for. We looked at how deep they were, what aquifer layer they were screened in or open to, and then we separated all of our results by aquifer layer so we can see how the unconfined aquifer is behaving and the 3 different primary confined layers. First, though, we did some data cleaning. So these are hydrographs just from random wells that we pulled. And first, I want to highlight that we are only using the spring measurements that represent the long-term equilibrium water level. So if a well had multiple measurements in a single year like this, we only took that highest water level to represent the spring. This does show interesting behavior here. So sorry, everything is in feet. This is 80 feet or 25 meters or so. And then it drops down to closer to 30, 35 meters. So that second data point was taken in the fall after irrigation. So it's quite common to have drawdowns due to the irrigation pumping. So we only took the spring levels and we only conducted our trend analysis for wells that had enough data to provide a robust trend. Okay, I am not expecting you to be able to see everything on this graph. I'm going to walk you through what you should care about. Okay, so first, in the upper left, we have the Grand Ronde aquifer layer. That's our deepest, most extensive spatially layer. Then we have the Wanapum, Saddle Mountain, and Overburden. So deepest basalt, next deepest basalt, shallowest basalt, unconfined. So the first thing that is obvious is that the spatial coverage of, and I should say, these are trends that we calculated from the year 2000 to 2020. So the trend in water level. We also calculated the trend from 1975 to 2020 to have a longer time frame, and the trends were statistically the same. So we used the more recent time period. So the first thing you notice is that the spatial coverage is really different across those different aquifer layers, right? And that's partially due to the fact that you don't have all 4 of those layers in all areas. So this area right here, if we think back to our history lesson, that is the portion of the Columbia Basin that is on temporary groundwater permits. So they are still experiencing declines of 3 meters per year or so. Now we have a big project to bring surface water back to this area. So we say this is the most spatially extensive declines, but then you see these dark red spots here. In this portion of the study area, we have compartmentalized flow. And so the steepest or the worst declines are experienced in discrete locations throughout the study area. So trends do not tell us the whole story when we want to think about future water supply reliability, right? If we want to ensure we still have groundwater in the future, trends only tell us how our groundwater has been changing, but not what is available in the first place. So anytime we do a study around water stress or water sustainability. My students who are watching this will laugh because I always say a water stress study, you have to quantify how much water is being used and how much is available. There are a million different ways to define what water availability is, right? For groundwater, you could compare how much is used to the total volume there. You could compare how much is used to the amount of recharge. It's a topic that people actually debate quite a lot for how to evaluate sustainable groundwater use. So we defined our availability term based on how deep your well is, right? If your water table is down here, your well can't access that water. So even if there's still water in the aquifer, it doesn't matter for you because your well can't access it, right? So we defined a term called available drawdown as the difference between the spring static water level and the bottom of the well. Actually, we said 20 feet above the well to estimate where the pump is located. We said this is the amount of water that our current infrastructure can access. And if the water level declines below that point, who cares if there's still water deeper in the aquifer if you cannot access it, right? So we assessed vulnerability then. We calculated the depth of the pump. Our well logs have a record of how deep the well is drilled. And then we calculated the amount of available, you could think of it available saturated thickness, available drawdown as the difference between the static level and the bottom of the pump. We used the trend to project forward what the water level will be in 2040 as required by our legislatively mandated project. And then we calculated the percent change in the depth to water between 2020 and 2040, and then also the amount of time it takes until there's a 25% reduction in available drawdown. Also with stress studies or sustainability studies, we set a threshold and we say, if the use to availability ratio is 10%, it's low stress. But that doesn't really mean anything. That's an arbitrary threshold. So we use 25% to represent when you might need to invest in your well infrastructure. Maybe you need to deepen the well. And then as you get more and more percent change, perhaps the well is going to go dry. So we did our vulnerability analysis based on this. And this map is showing in these red areas. These areas have 10 years until a 25% change in the depth to water. So we say in about 10 years, you need to think about your current well infrastructure and think about deepening the well. In reality, for different users, 25% change might be fine or might not be fine. And this is across all of the different aquifer layers, just to make this look really extreme, right? We just took the most extreme, the most vulnerable layer from the aquifer system. So overall, from this analysis of trends and vulnerability, the key takeaway is that every single aquifer layer has a different level of vulnerability and a different level of groundwater decline, both where you are vertically in the aquifer and where you are spatially. So if you're in the Grand Ronde, pumping from the Grand Ronde in this area versus this area, the trend might be different. The level of vulnerability might be different. And so when you think about managing this groundwater, you have to account for the heterogeneity in the aquifer system. You can't just call it one aquifer, right? That Grand Ronde, our deepest layer, has the most declines. This part is, I just summarized the main takeaways here. So then this brings the next question. Can our satellites detect these different changes within an aquifer system? Let's look. So first, we'll step back and think about hydrology applications with remote sensing. I'm not very good at PowerPoint, so please excuse my little graphics that I made in PowerPoint. Okay, here's the landscape. We have mountains, we have a lake, we have trees, and we have a whole bunch of satellites. These are satellites from many different international space agencies, not just NASA, the one in the US, but many different satellites. These are all of the satellites that can detect changes happening to what you see in my little graphic here. All of these satellites are only detecting changes either at the land surface or up into the atmosphere. So things like mapping land cover, temperature, reflectivity, vegetation indices, that's what these satellites are detecting at the land surface. None of these satellites directly help us to understand groundwater, right? So then we try a little harder, and we get SMAP, soil moisture, active, passive. This is not the first satellite to detect changes in soil moisture, but it is the most current one. Now, SMAP can only detect changes in soil moisture down to about 5 centimeters at best. Does that help us with groundwater? No, it does not. So, finally, we have GRACE. Let's do thumbs up again. Have you heard of the GRACE satellite? Thumbs up, maybe thumbs sideways, no thumbs down. Cool. I like doing that because then your whole class doesn't have to see if you don't know something. You can just, yeah. Okay, so GRACE, I'll talk about quite a bit today and in the mini course this afternoon and tomorrow. GRACE can indirectly detect changes down into the subsurface for an unconfined aquifer. We think down to the bedrock. For a confined aquifer, semi-confined aquifer. The key is GRACE doesn't know if changes are coming from groundwater or somewhere else. It's our job to isolate groundwater. So we'll talk about how to do that. But first, we'll do a little background on GRACE. GRACE stands for the Gravity, Recovery, and Climate Experiment. GRACE is a unique satellite mission because it's actually we'll start here. It was launched in 2002, and it's a joint mission between NASA and the German Space Agency. We generally start using the data in 2003. GRACE was initially planned to be a 5-year mission, but it outlived that time span. And so the batteries finally started dying, and the first GRACE mission stopped collecting data in 2017. And then a second GRACE mission was launched with the same technology in 2018, GRACE follow-on. GRACE has a monthly temporal resolution, 1 data point per month at a global scale, but only a large global scale. So the accuracy of GRACE is it can detect changes in the water budget of plus or minus 1 centimeter over 150,000 square kilometer areas or larger. So if you have water mass changes spread across an entire aquifer system, GRACE can detect changes of just plus or minus 1 centimeter, which at that scale is impressively accurate. Yeah? And GRACE is detecting changes, as with all satellites, from a combination of human and natural perturbations, right? Satellites are just observing what is happening on Earth. Everything happening on Earth is a combination of human and natural influences, okay? Initially, GRACE was launched, it's the Gravity, Recovery, and Climate Experiment. Initially, GRACE was launched purely to better understand Earth's gravity field. So on the left, this was our pre-GRACE understanding of gravity anomalies globally. And on the right is after GRACE was launched. So we have a better understanding now of where there are gravity anomalies, more or less mass, on Earth because of GRACE. So how does GRACE work? It's a pair of satellites, right? Again, most satellites, it's a single satellite that has different instruments on it, taking pictures, radar, whatever. The actual thing being measured for GRACE is simply the distance between the two satellites. That's it. And the location of the satellites. So the satellites fly around the Earth. They're about 220 kilometers apart. And as the front satellite comes up to an area with a lot of mass, a mountain range, let's say, that mass, from Newton's law of gravity, that mass pulls the front satellite down toward it, and the distance between the satellites increase. Now, let's say it snowed a lot in that month, so the next time the satellites pass over that same area, there is more mass because of that snow. Water is really heavy, so large changes in the amount of water have significant impacts on Earth's gravity field. We call it the time variable gravity field. So it's just how gravity is changing from month to month to month, not the total amount of mass in the first place. So this afternoon, we'll talk about how you have to subtract out the mean because we don't know what the total gravity is, only the changes in gravity. Okay? And then they separate again. So the satellites come together, then they separate as the front comes up to a lot of mass, and then they go back together. And then those changes in distance get mapped as gravity anomalies on Earth. On a monthly timescale, it takes about a month for the satellites to get full coverage of the Earth. And then those gravity anomalies are converted to water mass anomalies because on those shorter timescales, water mass changes, again, are the main thing influencing changes in Earth's gravity. Do you all know Tom and Jerry? Are you old enough? Okay, good. So the GRACE satellites are nicknamed Tom and Jerry because they chase each other around, yeah? When I was a kid, I would watch Tom and Jerry here in Brazil. Okay, so the way we apply GRACE to hydrology studies is by thinking about the water budget. So this is now the full vertical water column. All of the places water can be stored on land, the terrestrial water budget, mountains, soils, surface water, down into groundwater. So GRACE is measuring or quantifying changes in the amount of water stored in this whole water column. And we can write that in two ways. Have you learned the water budget in geology? Okay, it's easy. The math with GRACE, very easy. You're just adding some things together, right? So first, you'll notice this delta here. That represents an anomaly. So whenever you work with GRACE data, you subtract the mean, and what you're left with is an anomaly, right? So everything we look at, all of our time series are, do you have more or less water than average? And the total anomaly, total terrestrial water storage anomaly, is just the sum of anomalies in snow water equivalent, surface water, soil moisture, and groundwater. So we say that this is the stocks-based approach to quantifying the water budget. The other thing you can do is the flux-based approach, where from month to month, now we have d by dt, right? D over dt. It's a time derivative. So now it's the difference between months, February minus January, March minus February. And that is precipitation in minus evapotranspiration minus stream flow plus lateral groundwater moving in minus lateral groundwater moving out, right? So to recap, again, GRACE is measuring either anomalies or storage change in the total amount of water stored on land as the sum of either the fluxes or the stocks, right? And then it's up to us to figure out what GRACE is actually being driven by. So is it mostly because of groundwater that we observe changes? Is it mostly changes in stream flow? Is it mostly from human reasons or mostly from natural climate variability? All of that is wrapped into these simple equations, right? Mathematically, using GRACE, very simple, but in reality, it's very complex to understand what is driving the GRACE signal, yeah? So here will be a little video, and we'll do this first. This is the state of California. We have the Sacramento and San Joaquin River basins in yellow, the watershed areas in yellow. And then on the left, this is the basin averaged time series. So often with GRACE, we look at the data in two ways. One is the spatial maps of storage change, and one is the basin average of your study area. So across an entire aquifer, across an entire river basin, how is storage changing? So on the left, we will watch the time series. Anytime the storage is increasing, the map on the right will be in blue. Anytime storage is decreasing, the map on the right will be in red, and we can just watch how these change together. This is a multi-year drought for California. Things got very, 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 very bad. And then it snowed a lot. And it came back up close to normal. So GRACE allows us to actually quantify those changes, right? In groundwater, GRACE is amazing. It's magical because it gives us a total integrated measure of groundwater storage change, right? Historically, we have to take point observations like I showed earlier and interpolate or do smaller scale geophysical studies. And this way we get a whole aquifer all at once. But again, we have to figure out what is going on to drive this signal. Okay, so then how do we apply GRACE to the study of groundwater? We all feel good about subtraction, I'm sure. You just go like this. So the left-hand side, first, this is the total water storage anomaly. That is the only thing being observed directly by GRACE. And then you can just subtract out groundwater. And in order to do this, so we then have GRACE data, we need other ways to quantify these other terms, right? And so often to quantify snow water equivalent and soil moisture, we have to rely on models. Models historically are not always great at simulating things like soil moisture storage changes. Most of the models only go down to 1 meter or 2 meters depth. So the only water being simulated is to that depth. In some places, we have direct observations of snow, sometimes of soil moisture, but again, those are always point observations, right? So then you have to interpolate to the scale of GRACE, which is really big. And then hopefully for surface water, we have observations of lake or reservoir storage change. So this is how we use GRACE to study groundwater. You take GRACE and you subtract out everything from the water budget that is not groundwater. And then we call that the groundwater residual. The part that is left, the residual, we assume is groundwater. What is also actually in that groundwater signal right here is all of the uncertainty from the other methods that gets propagated into that groundwater residual, right? So we try to do error propagation, but that always has its own uncertainty, right? So we get this groundwater signal. Just a little history of how GRACE has been used, what put it on the map. These are two images from the first GRACE paper that was published to really look at groundwater. The study area is in northwestern India, right up here. And this was the first time we disaggregated or separated out the GRACE signal into the parts of the water budget. And so they used models to isolate out soil moisture. In this area, they assumed surface water and snow was negligible, and then had the groundwater line in blue and then fit a trend. So they were able to, for the first time, quantify the total amount of groundwater that had been lost. In this case, I believe it was 109 cubic kilometers of water just over 3 or 4 years. What's their time frame? 2002 to 2008. So in 6 years, they said 109 cubic kilometers of groundwater was lost using this method. This method has then been repeated in many, many, many other study areas. This is from California. I use this. This is from my PhD. I use this general approach to quantify stress in the world's 37 largest aquifer systems that you see here. One problem, though, is that these are all basin averages, right? Monthly basin averages. That means that for every one of these giant aquifers, we have one data point for the whole study area per month. We can pull out the High Plains or the Ogallala Aquifer from the central portion of the US right here. This is an area that is well known for groundwater declines. And if you look at the spatial map of GRACE, you see that there's a huge difference within the aquifer. So in the north, this is the recharge area. This area is gaining water. In the south, it's losing water. So it's always important to look at the basin average for your total constraint, but also what is happening inside the system. So then on the bottom here, there have been a number of validation studies to compare GRACE-derived groundwater to groundwater observations, okay? So GRACE is in red, and then in blue is 2 different methods to interpolate point observations. But in order to convert from water level observations to a storage change, you have to multiply by a storage coefficient. So for unconfined, it's specific yield, right? And often, I think, these validation studies pick those coefficients that make the results look good, in part because we don't have great data in many places on what that storage coefficient should actually be. So we'll say, using specific yield of 0.2 for this entire aquifer system, we compare observations to GRACE. So that's fine as a starting place, but we need to do better to understand how well GRACE is actually representing the ground-based observations. We do other stuff with GRACE. I'll skip that for now. All right, let's circle back to where we started in the first place with the trends and vulnerability in my aquifer. So I asked this question, right? Is GRACE able to capture the storage changes in this mostly confined aquifer system? So our methodology, we started with GRACE. We used model output. I'll talk about that in a moment. And then we have direct observations of all the reservoirs in the area. So we use these data sets to isolate out groundwater. And then all of the little red dots here, these are all of the locations where we have well observations across this entire aquifer system. So not just the Eastern Washington portion. Now we're expanding out to the whole Columbia Plateau regional aquifer system. So our goal is to isolate out the GRACE groundwater signal and compare it to the trends from the first part of the talk. Are they the same? Are they not? I'm just going to skip through this. We can go over the details if you want. The key here is what's in the bottom. Groundwater storage anomalies equal your storage coefficient times your groundwater level anomalies, right? The depth to water that you measure in the well does not directly translate to the amount of storage loss you actually have. So a water level change is related to a storage change by the storage coefficient. And in the Columbia Aquifer, these are the storage coefficients for our different aquifer layers. So remember, the overburden is that unconfined layer, and the other 3 layers are 3 different confined basalt systems. The first thing you notice with those numbers, and those of you familiar with confined and unconfined groundwater know that the storage coefficient for confined is much, much, much smaller than unconfined, right? So then if you look at the equation, if you have the same change in water level in a well between unconfined and confined, you lose more storage from unconfined than you do from confined, right? Was that confusing? You got it? Okay. So GRACE needs a big enough storage change signal to detect anything, right? So we're curious if the confined storage changes are large enough to actually be detectable by GRACE. And I'll just step back and say, I should have had a slide on this, but part of the importance of this work, I think, is that many, many GRACE studies that are studying groundwater do this, right? They isolate groundwater, they calculate a trend, and they say, this is how much groundwater is being lost, like in India, right? And often that is attributed to confined or non-renewable groundwater, right? That's a very flashy headline. We're losing so much non-renewable groundwater. But non-renewable groundwater is confined. And we don't know if the storage changes in confined aquifers are actually large enough to be detectable by GRACE. Okay, just a quick side note. As I showed in the beginning, our study area has a lot of cropland, and most of it is irrigated. And we thought, well, when you irrigate crops, you influence soil moisture. And if we're using models to subtract out soil moisture, we need to represent crops. Most models used in GRACE studies don't represent different crop types or different irrigation types. Agriculture is just one land cover and is treated the same everywhere. So at my university, others, not me, have connected a hydrology model to a cropping systems model that simulates over 90 different crops in the Columbia Basin through different crop growth stages. So the hydrology model says, this is how much water there is naturally today. The crop says, this is how much water I'm using, and returns evapotranspiration to the hydrology model. So the agricultural system is updating our soil moisture estimates. We thought that would make a big difference in isolating out groundwater. It didn't actually, because of the anomalies, right? So this is just picking a random irrigated cell and non-irrigated cell, just random, not necessarily representative. So of course, when you apply irrigation, you have more soil moisture. That's why the line is shifted. But then when you calculate the anomaly, you remove the mean. Statistically, the irrigated or the crop growth model results are basically the same as not having crop growth in a model. So that's good. And we evaluated model output to point observations of soil moisture, and we feel okay. Okay, so this is the classic disaggregated GRACE signal. So in the upper left, we have total water storage anomalies from GRACE, and you see the gap between the first satellite mission and the second one being launched. We have soil moisture anomalies, surface water anomalies, and snow anomalies. When you work with GRACE data, one quick check that you have processed your data correctly is notice how everything is hovering around 0, right? On the y-axis, 0 is in the middle. When you subtract the mean, everything should hover around 0. You're taking the mean out, so the average should be 0. So step 1 in working with GRACE data is to ensure you've calculated your anomalies and everything's hovering around 0. All right, the other thing we see here, and all of the y-axes are the same scale, I should add, the majority of the GRACE signal from the water budget components present is from soil moisture. So about 30% of the GRACE signal in this time frame is coming from changes in soil moisture. And using the GRACE groundwater residual method, about half of the storage changes from month to month are from groundwater. So we wanted to compare those GRACE results to all of our observation data. If you recall, we only have observation data mostly once per year in the springtime. So instead of being able to do a monthly analysis, we are doing an annual analysis. So we averaged everything to be spring. So we have GRACE, annual spring anomalies, soil moisture, snow, and surface water. And now we've added uncertainty bounds. And then we can calculate, oh, sorry, this is back to monthly. So these are monthly anomalies in groundwater. It's great. You get a time series. You can start talking about the seasonality. Wait a second. There's two lines here. That's the model with crops and the model without crops. There's just one line though. How many aquifer layers do we have? How many layers do we have? Do you remember? 4? It's our 4-layer cake, right? But there's only one line. So GRACE is detecting all of the changes across all of those layers in just one single time series. So we wanted to compare what was going on with the GRACE-derived groundwater to the individual aquifer layers. So now we have again separated out all of our point observations into our different aquifer layers. So again, red is Grand Ronde, the deepest layer with the most extensive groundwater declines from our trend analysis. Ideally, we could do this analysis with pressure transducer data to have higher temporal resolution. We just don't have enough data. The green dots here are where we have pressure transducers located. I'm working on getting a lot more so we can look at monthly dynamics of all of this. But for now, we just have annual. This is just a reminder of the trends by aquifer layer. And then we converted those water levels observed into storage change using these same storage coefficients. Then we calculated a basin average, and let me walk you through this graph. So this blue line here has the right-hand y-axis. This is the sum of only the 3 confined aquifer layers. Okay. GRACE-derived groundwater is the red uncertainty bars. These are 95% confidence intervals, and the stars. And then the circles is all of the aquifer layers together, including the unconfined. Remember that most of the pumping in our system is from the confined layers. All of our concerns about water supply reliability and declining trends and McDonald's potatoes are all from the deeper confined layers, right? All right, so first, on the y-axis, we have liquid water equivalent, so the amount of water changing from the mean. And you see that the scale is really different, right? So the GRACE scale goes up to 25 centimeters. The confined only scale goes up to 0.06 centimeters. We immediately notice, as we expect, that the confined layers alone are observing a decline, right? Over this time period, the line is going down, that trend is declining, and is a statistically significant trend. I'll show the trends in a moment. So then what is GRACE seeing? Is GRACE capturing any of what is actually being observed? So first, we notice some places comparing GRACE, which is theoretically all of the layers together, to the observed, all of the layers together. And in these areas, in these circles, our lines are out of phase, right? GRACE is saying that groundwater is more than average. and the observations are saying that it's less, and then it flips, right? So GRACE is showing the opposite of what our observation data is showing. I thought I had some more little circles that pop up. I suppose not, so I'll walk you through. All right, so we have our confidence intervals here, right? When confidence intervals overlap, they're statistically the same, right? If you have two confidence intervals from two different data sets, you cannot say they're observing different things. And so we see that in a few places. So here, 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 right? So we have a few years where GRACE is statistically capturing the same thing that the observations are showing. But in all of those other years, our confidence intervals are separate, right? So statistically, GRACE-derived groundwater is observing something different than what the actual ground-based observations are saying is happening. And then we can look at the trends. So our trend in all of the confined system is statistically significant. The trend in all of the observed groundwater is statistically significant to the 95% level. The trend in groundwater is from GRACE is near zero, and that is statistically insignificant. And then the overburden trend, that unconfined, is positive. Okay, so all of these different layers are showing something separate from what GRACE is telling us is happening. Are we surprised? Not necessarily, right? If you think about the size or the magnitude of the storage coefficient to convert even severe water level declines to a storage change, it's still a small amount of storage change, seemingly below the detection limit of GRACE. So when we use GRACE to study confined groundwater and you see a big depletion trend, the very first thing to do is not assume we're pumping from a non-renewable water supply source and this area is going to be terrible in the future. The first thing to say is, what other uncertainty do I have in this analysis? And is some of the declining trend not actually non-renewable groundwater, but something else? Maybe uncertainty propagated through the other data sets we use to isolate groundwater. Okay, so a few reasons why we might have these differences in addition to what we've talked about. Maybe we have some incorrect assumptions of the conceptual model of our different layers. We were talking yesterday about the wells in the basalts. Many are uncased. So there's a lot of, we think, there's a lot of flow across the aquifer layers. So some of the trends we're observing, we don't actually know what layer they're coming from. It could just be one layer draining into another and not resulting in a storage change. The GRACE data has signal leakage, so you can't just take one single grid cell of GRACE data and use it. The larger the spatial area, the more accurate the GRACE results are. And so this aquifer is sort of at the spatial limit of reliable GRACE data. So maybe there's signal coming in from outside that is influencing what is coming up as groundwater. Maybe we still have not enough groundwater observations or poor storage coefficients that need revising. This is just what our old well logs look like, so sometimes it's hard to see what's going on. Maybe some of the storage loss is coming from outside of the aquifer system that is contributing to the GRACE signal. And then to deal with the issue of sparse data, I'm developing a community-based monitoring network. So we have these units called conservation districts. They're semi-government organizations that work with farmers to help promote land management. And so we have trained them and provided equipment on how to do groundwater monitoring, especially in areas that don't have a lot of groundwater data. So this map all of the gray dots in the red are locations where groundwater rights have been issued. So people theoretically are using groundwater. And then all of the blue blobs are locations where we have monitoring data plus a radius around that. And so we definitely have areas where we have groundwater permitted for use, but that we don't have monitoring data for. So that could be influencing our analysis. So what does that tell us? Oh, this is some of the new locations that we are monitoring. Careful how you interpret data. Okay, so how should we think about the role of GRACE in studying groundwater? GRACE is great at highlighting hotspots, right? Based on what we've seen, if an aquifer system or a river basin shows up as having a negative trend, then you should pay attention, right? But even if an aquifer system shows up as having a near zero trend, like my aquifer, that doesn't mean you should walk away and not care, right? So GRACE shows my area as a near zero trend. We have farmers and communities whose wells are already running dry because of water level declines. It's just that those declines are not captured in the GRACE signal. I still think there's interesting opportunities for how to use GRACE as a constraint on sustainable groundwater management. If you have a negative trend, more water is being lost than is being put in, right? There's overuse somewhere. So I think we can still use GRACE to constrain how we manage large-scale groundwater. We can use it to help parameterize groundwater models and land surface models. And GRACE plus models are still very useful tools in data-sparse areas, right? The Guarani, the Columbia Basin, we have a remarkable amount of data compared to most groundwater systems. In areas where you don't have that, GRACE and models, they're global, right? So you can still use them, but we need to use our areas that have a lot of data to understand how better to apply these GRACE methods where we don't have data, right? I think another thing that is very, very important that the GRACE community can improve on is being transparent with what assumptions are being made. It can be often quite hard to figure out if an aquifer system has an unconfined layer, confined layers, or not. Many data sources don't say if a water level observation is coming from unconfined or confined, or how deep the well is. So a lot of assumptions are made to use these data that may or may not be appropriate, but they're not stated in the first place to evaluate. So we really have to be clear on how we are using the GRACE data and consider vertical and spatial heterogeneity within an aquifer system. So these are the tools. We didn't actually talk about this, but groundwater models. There is a groundwater ModFlow-based groundwater model of the Columbia Plateau. It's only on an annual time step. We're in the process of converting that to monthly, and that will be another nice evaluation tool compared to GRACE. There's huge opportunity to incorporate more geophysical methods, in part to span the spatial scale between GRACE, which is huge, and wells, which is very small. I'll just end with some playing around ideas of how else we can use GRACE. This is work from a master's student I had who was supposed to come work with Didier, and then COVID happened and he didn't come. And so his work has just sort of paused. And an important note, I am learning about these areas, please help me. So we did the analysis, we made graphs, we can talk about them, but we don't know this area like you all. And so we need your help in interpreting what makes sense physically and what does not make sense. Okay, so first we looked at the river basins that were large enough, that had long enough time series to do anything with GRACE. And we started with the water budget equation. I love fundamental equations, so we started at the basics. But often this is the water budget equation that gets used to estimate changes in water storage. Obviously, the difference between equation 1 and 2 is that groundwater has dropped out of the second equation. Usually we say, oh, the fluxes of groundwater are too small, they're negligible, so we ignore it, or it's in steady state, and so they cancel each other out. And we were curious to use GRACE to actually test some of those assumptions that the groundwater storage change is zero as the lateral fluxes of groundwater. And so we just took the total GRACE signal and subtracted this surface budget that we quantified using remote sensing and ground-based observation, so no models here, to quantify what this groundwater flux would be for all of these river basins. And these are a little hard to see. On the bottom is precipitation, evapotranspiration, and streamflow. And I have this in a table. But on top, we have GRACE in black and the surface water budget in blue. So where those are the same, you can assume the groundwater flux is negligible. And where they're different, you can assume the groundwater flux is relevant and shouldn't be ignored. It might be easier to see it in this table. So all of these watersheds, we quantified a non-zero flux of groundwater change. But again, this is where I would love feedback for what makes sense and what does not make sense. We have these plots here. The solid line is the one-to-one line. The surface water budget is on the y-axis, and GRACE is on the x-axis. For the most part, you see that these points are above that one-to-one line. So the surface budget is higher, more water, than the GRACE budget, hence having a flux term of groundwater. So that's one way to play around with GRACE. This is my last section. Another thing we wanted to do was look at the Guarani and see if we could do anything interesting, right? The nice thing about thinking about the Guarani compared to the Columbia Plateau is both are predominantly confined, fairly well mapped and monitored groundwater systems. And so first we did that method of isolating groundwater from GRACE, this time using models. And the blue line here is the monthly groundwater storage anomalies compared to GRACE in black and soil moisture in yellow. This is this spatial map. So this is trends, 95% confidence of groundwater anomalies. And here, I apologize that the color scale is flipped. So anything that is yellow, the groundwater trend is positive. Anything that is negative, the groundwater trend is blue. Curious if this makes sense based on where things like pumping are occurring. We did the trend on the other water budget components to see what else is going on. So we see that same area is a positive trend in the total GRACE signal, but the other components of the water budget don't really have much going on. And then we thought, oh, wouldn't it be fun if we could estimate what the head changes would need to be in order for GRACE to be accurate. Does that make sense? So we took this equation, the groundwater storage anomaly is the storage coefficient times the head change, and we separated out just an estimate of how much the pumping would be coming from the shallow versus deep part of the system. We used a specific yield value from the literature. We calculated storativity in part with thickness data from Didier. And right, this is all purely hypothetical, right? I'm not saying these are the observed head changes. Want that to be clear. So if 95% of the pumping is coming from the shallow system, then the head changes in the deep confined portion would be plus or minus 15 meters per month. So if GRACE is capturing confined pumping, that is the magnitude that the head changes would need to be for GRACE to be accurately capturing the confined pumping. If 99% is from the shallow, then we go back to plus or minus 0.4 meters of head change for both the confined and unconfined. And then if almost all of it is from shallow, then we have really small confined changes. So this is just sort of a different way to think about if GRACE is accurately capturing head changes in confined systems or not. So then the next step would be to look at observed head changes and see how they relate to these head changes, and knowledge of how much pumping is coming from shallower portions of the aquifer versus deeper. Okay, so just fun things that you can play around with data from far away and then need somebody local to see what actually makes sense. I will end here. Later, I can show some slides from a study on social science monitoring of groundwater in Ceará, but for now, maybe I'll pause. And I think this is a funny joke if you're a hydrologist. Thank you. And if you have a question in Portuguese, I have a personal translator to translate to English. Okay.
Hi, doctor. Thank you for the lecture. It was very interesting. I am a computer science student, so it was all very clear because in the technology area, we are not like, we're not, gosh, we are not familiar with this kind of data daily. And I was wondering, I have two questions actually. I was wondering, first, the results you encountered in your area of study there in the United States, you think it could relate to other places in the world? Like, and the second question, the results you found, usually in the daily basis, like for most of people, we always talk about how water is important and we need to start saving it and start caring for it even more and more. But people always talk about surface water because it's like more common sense and more accessible for all people. Do you think the groundwater issue is like as big as the surface water issue, and we should start talking about it more and exposing to like normal people?
Do you have a phrase here, a softball question? Is that a phrase in Portuguese? No. Okay, good. So in the US, we say a softball question is a question that is very easy and lovely to answer. So you can make a friend ask a softball question so you look good, right? So it's a question I love to answer. So your first question, are the results in my study helpful for other places? I hope so. In different ways. So one is, as I said, I think GRACE and models are very important tools in areas where we don't have ground data. And so areas like my basin, the Guarani, where we know what's happening, I think we have a responsibility to better evaluate GRACE and quantify the uncertainty in our common methods, right? So we can quantify uncertainty compared to observations in our confined systems. And then if we use this method somewhere else in a confined aquifer that does not have data, then we better know what those uncertainty bars are, and we better know the assumptions and the limitations of the analysis. So I think one important thing is using these as test areas to improve how we use our methods in areas that are also confined. Our study area is a little bit unique in that we have the multiple layers, and it's a basalt aquifer system. And so most of it is hard, dense rock, and the water moves through cracks and fissures and separations between the layers. So the flow dynamics are different, and the compartmentalization, the way water is different here versus here might not be the same in other types of aquifer systems. So our methods are most appropriate to apply in other basalt systems, for example, in portions of India. So the hydrogeology is different here for the Guarani than it is in Washington. If you're thinking about how the system recharges and if you pump from here, how does it influence here? So that is different, but there are other areas that have fractured basalt aquifers. So some of our methods can best apply there, but really as it relates, I'm talking fast, as it relates to GRACE, I think it's really testing our methods and making sure that the way we use the data and interpret the data is actually appropriate for confined groundwater systems. Your other question on how much we talk about surface water versus groundwater. I joked earlier that it's much easier to study rivers, and everything is hard, right? There are different challenges no matter what you're studying. But we have a saying, you can't manage what you can't measure. And so with groundwater, if we don't have data to observe what is happening, it's hard to tell a manager that we should manage groundwater better. And increasingly, people are becoming interested, at least from my perspective, in groundwater and becoming more aware that it is not a magical pool of water that will last forever. So I think GRACE has helped contribute to that, but not only GRACE, just water scarcity that we see is raising the profile of groundwater. But one big issue, when I was in graduate school, my advisor and I went to Washington, D.C. a lot, and we talked to congressional members about GRACE and groundwater and depletion. And my advisor would be talking a lot and saying, this area's screwed, this area's screwed, red, bad, groundwater declines. And they would just stare at him, and I'd pause and say, do you understand what groundwater is? Often not. So I think some of our challenges with groundwater are so fundamental in how we manage it better. It's what is groundwater in the first place? What is a water table? What is the difference between confined and unconfined? So I think we have some basic education to do, but I do think it's becoming more popular. One of the things I've done that I didn't talk about was a partnership with an economist. And I thought, what makes people care about stuff? Money, right? And so we are working to quantify the economic value of groundwater depletion, or the economic value of having groundwater in a drought year. So for us, if a drought has been declared by the state, then you can apply for emergency groundwater permits. And so we're trying to understand how much value that additional groundwater permit adds to farmers in a drought year. And what we find is that the high value crops are the ones that use groundwater for drought, right? You can stop growing, you can exchange water with a neighbor, you can pump groundwater when there's a drought. Apples, grapes, hops for beer, these are the crops that would turn to groundwater, which are all high value crops. So for example, in 1 year, the emergency groundwater added $600,000 of profit estimated compared to if that groundwater had not been used previously. So I think we can get creative in how we represent our groundwater information to make people care, right? Sometimes I say a time series is the squiggly line plot, right? Not everybody is trained to look at a time series and see what it means. But if you look at a dollar amount, people understand that. So I think we have an opportunity to present our information in different ways that can help highlight the importance of groundwater, so we can try to catch up on how we talk about groundwater compared to surface water.
Thank you.
Yeah.
My question is about the function of the grace because I don't really follow. The path that the grace does in the sky is the same all year, or the path changes because that will make difficult to measure all the world, you know. And another question is that one of your slides showed 4 graphs with a gap that you say that is when the satellite was launched, but I really can't follow what happened because it shows as a circular date. If you can explain again.
Thank you. Nice English. The first, both of you. So the first question is the path that the satellites follow. So we say that GRACE is on a polar orbit. So always it goes North Pole, South Pole, North Pole, South Pole, North Pole, South Pole. And it takes about 10 days of moving around to get an initial coverage of Earth. And then it takes the rest of the month to fill in a full coverage of what is being observed on land. So there are 4 to 5 different places where you can download GRACE data from. I don't convert from the distance of the satellites to gravity anomalies to water mass anomalies. Other people do that. But one of the centers has a GRACE product that is a 10-day time step, because in 10 days you can mostly cover GRACE, but then it just fills in all of the gaps continuously. And in about 1 month, it has a fairly complete coverage. But it's true that then that's a source of uncertainty too, right? If you're not always in exactly the same place at the same time, or you have a map that represents January, but Washington, the satellite went over on the 5th of January, and Brazil, the satellite went over on the 17th of January, right? So it's not exactly the same. That's something we just have to acknowledge. And then your other comment, so there are batteries that power the laser that measures the distance between the satellites. And the lifespan of those batteries was planned for 5 years. And over time, batteries die, right? And so actually throughout the grace period, there are months when we turned off, I didn't have anything to do with it, when the batteries were turned off and did not collect data in 1 month in order to preserve the battery for longer. But eventually the battery just died. And so the measurement of the satellite distance could not be continued anymore. And then the lifespan was over of the satellite mission. But they had been building replacement satellites, the exact same design, exact same everything, that was then launched in 2018, the following year. So the time in between was from when the batteries of the first mission died until the second mission was launched and started collecting data. Yeah? Okay.
So thanks for your talk. It's amazing. And thanks for coming also.
Thank you.
My name and in the name of the organizing committee. I have a few comments and I don't know if I have a question. I have one question. This is interesting. The emphasis you gave for the basic equation. So when you think on water budget, we should think in an easy way. This is important. I guess this is the most important lesson for your talk. The second one, I love your vulnerability decay index, because simple way to talk with managers is easy to calculate, to say, okay, you are in a good situation or not. And I like this kind of index. And many times you try to make things complicated, and this way is amazing. I text Carolina to look for that. It is interesting. My question is about your student's thesis on Guarani. So you show something very interesting. For me, it makes sense, but I have one question. So you have a decay in storage in the north and in the south.
Yeah.
In the north, we have an unconfined aquifer. Basically, it's a sandy aquifer that is losing water. Probably you capture this signal instead of capture the signal of the confined units.
Yeah.
In the south, we have basalt that also is losing water because we are looking for the decay on the flow rate in the rivers, so we don't have no more base flow because of distraction of this basalt layer. But something very interesting is in the middle where you gain water.
Mm-hmm.
This is exactly the point where you have a very important geological structure in the basin. You have a dike of diabases, and when you talk about gravimetry or density, it's a more dense region of the aquifer. And my question is, it is possible that Grace is capturing this variation not in storage of water, but in variation in density of the rocks.
I love this. But would that variation be time variable, or is it constant? Right?
Is it constant?
So then it should be removed when we calculate the mean. So calculating the mean gets rid of the mountains, gets rid of features like that. Anything where the mass is not changing over month or even multi-year, right? If it's changing over thousands of years, geologic formations, then it would show up in the mean that we subtract out.
Yeah, this is interesting because I don't know. I never think about this like Ponta Grossa arc as a kind of water divide or groundwater divide.
Yeah.
Yeah, for us when we think on groundwater flow for the Guarani, make more sense as a barrier than a divide.
Yeah.
Where some recharge can happen. We should think about that.
Yeah. And then also that's where I always tell my students to think about the methods before trying to explain something, right? So it could be that the models we used to subtract out from Grace and isolate groundwater, maybe the models for some reason have more uncertainty in that area. So some of it could be error. That said, I only showed the statistically significant trends. So the error would have to be quite large. And often we assume and proven the trend in soil moisture is usually negligible, right? The amount of soil moisture from year to year does not really change to significant degrees. And so probably it is not from soil moisture. Snow, thankfully, not a problem. That makes things easier. Yeah, so it will be fun to think about what is happening. Yeah.
And another comment or maybe a question. First study published with Grace is in the Amazon basin. And I guess at that time they are more interested on the surface water budget. And now we are trying to remove the signal of surface water, but in some case, do you have an advice for who is working with that? When is important to remove the signal and when is not important to remove or to keep the signal in the water budget?
Right. Yeah, I mean, that is a very active interest of mine. And so similar to what we did in the Paraná and the other basins, right? If we have good discharge data, we can try a similar thing where you have all of grace and subtract out P minus ET minus Q and see what's left. Maybe this is where I would finally collaborate with my dad, because he does ADCP, velocity discharge measurements, at the mouth of the Amazon downstream of Obidos after Tapajos. So we could use observed stream flow, precip and ET, and see what the difference is, and see if there's a statistically significant amount of groundwater in, groundwater out. Yeah. And I think it's been fun working with Bruno, how to use this in a wetland area where there's so much groundwater surface water exchange, but not as much data as we want. So how can we accurately call something a groundwater flux to surface water or not? And yeah, how do we use grace in a wetland area where we don't have clear boundaries between surface water and groundwater? I think it's very interesting. Yeah, it's been fun to think about that. So I think it's a very open area of study. Absolutely. Está com fome?
Well, since everyone speaks in English, so I'll risk it too. In the name of the organizing committee, we'd like to thank you again for coming all the way through here from the United States. I think your presence really enhanced our meeting, your presence during the whole week. I hope we were able to make you feel welcomed in our country, in our institution. So thank you for sharing your knowledge with us, for your availability, and all your dedication to our event. Thank you very much.
Thank you too. I love being in Brazil. I love being here. You are all, yeah, wonderful, and thank you.
Now we have a little gift for you.
Oh. Thank you so much.